So I get to edit this part out every time. All right, so today we're going to talk about log functions and their graphs. That's not a bad way to font, is it? So why do we use logs? Because if we were going to solve an equation like this, can we get the same base on both sides? We could say that 2 to the x equals 2 to the 4th, and then we know that x has to be 4. But what about solving this one? Do we have a prayer, even in a Catholic school, of getting the same grades? No. So we have to somehow have the ability to take the variable out of the exponent. So that's why we like to learn about logs, because it helps us, besides the fact that the log function is the inverse of the exponential, but logs help us solve equations. So we can take the ln of both sides here, but we could also take the common log, which would be base 10. So we can say log, and when we use the common log, we don't write 10, which is it's implied. 10 to the x equals log base 10 of 150. And then we use our properties of logs, and we know that we can bring that down in front, and we get x times log base 10 of 10. And if you recall from last year, if you raise the base to some number and get 10, what does that number have to be? 1. So this is going to equal log base 10 of 10 is just 1. Because that's the exponent you raise 10 to get 10. All right, so x then here equals log base 10 of 150. And we could do this on the calculator. On the 84, because we have a log button. On the 89, they don't have a log button because natural log is better. That's bias, I know. All right, so I'm going to take the log, which is the common log of 150, and press enter, and there we go. All right, so it allows us to solve for x in this case. So it's got a really good utilitarian value there. So the bottom line is, if you remember this, I can't spell. How do you spell log?
I think that's it.
Are exponents. Okay, they're exponents, and I'll show you why. All right. So let's do y equals. Let's try an easy base, 2 to the x, and let's graph that using some points. Okay, so we're going to say x and y here, and let's use some nice points. I think I used 0, 1, and -1 to graph this. So what do we get when we plug in 0? 1. We plug in 1, we get 2. And then 1/2. So if we were to graph this function, at -1, we're at 1/2. At 1, we're at 0, we're at 1, and at 1, we're at 2. And so there is my 2 to the x. So let's do what we like to do to find inverses. So if I put x here and I say y inverse, what are we going to do to get that? We're going to just switch these points. So we're going to put 1, 0, 2, 1, and 1/2, -1. So let's plot that function. That function is going to pass through 1, 0, 2, 1, and at 1/2 we're at -1, sorry. And so this is the graph of the inverse, which is reflected about what line? Y equals x. So here's my y equals x reflection. All inverses are reflected across this line. And so we're going to define this as log base 2 of x. So that's its name. Now, what I'd like you to see right away is what are the y values here? The y values are the x values here, but the x values here on 2 to the x are the exponents. So the log function is a graph of all the exponents. Okay? So these y values are the exponents of 2 to the x, which is kind of interesting, I think. All right, so let's talk about the properties of log base 2 of. All right, what's the domain here? Zero to infinity, exclusive, because what's happened to the horizontal asymptote here for the exponential? When we switch it, the x and the y, the horizontal becomes a vertical asymptote. So it's exclusive on the domain. What about the range? It's all real numbers, yes. And if you look at the domain on the 2 to the x, it's all real numbers, isn't it? And the range is 0 to infinity. And since we switch the x and the y, the range would naturally also follow. Be switched. The domain of range on the inverse, okay? What about this function? Does it have any extrema? No. No extrema. Is this function continuous? Well, let's think about it.
Yes.
It's continuous from 0 to infinity. Now, it's continuous because when the second I put my marker on the board, I don't know why I wrote it twice. it's Wednesday morning, right? All right, so it's continuous from the second I put my pen on the board until I go to infinity, right? Do I have to pick it up at all? No. So it's continuous. I just want to make sure, I guess, that you think it's continuous, right? Making doubly sure. Thank you for that. All right. The symmetry here. It's none. Now, it's meaning it's neither even nor odd. Increasing intervals. That's right, it's an increasing function, which means it's, what is a word I'd like to use?
Growth.
I'm gonna use this word. Monotonic, meaning mono means one, tonic means tone. So it's got one tone, which means it only has one, it's increasing only. So monotonic functions are increasing only or decreasing only. The exponential is also monotonic, and so is the log. Okay? Decreasing, never, right? Not applicable. All right. Let's do the end behavior limit. So the limit as x goes to infinity of our f of x here is infinity. Good. Now watch it here. The limit as x goes to negative infinity. Does my function exist at x equals negative infinity?
No.
No. So that means the limit will not exist. So we're going to write this as dne. Okay? And then I have a vertical asymptote, don't I?
Yes.
And that was at x equals 0. So let's do the vertical asymptote limits. That would be the limit as x approaches 0 from the positive side, and the limit as x approaches 0 from the negative side. So I'm going to bring the curve down here so we can refresh our memory here. There it is. So what happens as x approaches 0 from the positive side? The function is approaching negative infinity. And what about as I approach it from the left side? What? It does not exist because it's not on the left side of 0. So we would say this one does not exist. And then the last thing I want to ask you about it is this function bounded? Yes.
The one that's not converted or the end behavior limit, why is 0?
Why is it does not exist? Because does this function, if I'm standing at x equals negative infinity, if you look up and down, do I have a y value over there? So it doesn't exist on this side. Does that make sense? All right. What about the boundedness? It's not bounded, is it? I'm not suppressing the y values in any way, so this is not bounded. All right. So what we've done now is we've kind of added a domain danger because this has got a restricted domain, doesn't it? So let's talk about those domain dangers. That's what you call them. I'm adopting his word. Or I call them gotchas. So the first one is 1 over something, right? What has to be true here? The something can be equal to 0. The second one is the even root of something. So what do we say here? That's right. So that can't be negative, but it can be equal to 0. All right, what about 3? I'm going to have an even root in the denominator. How does that switch things up? Yeah, this now has to be greater than 0. And now I'm adding a fourth one to the list, and it's the log. Base b, it doesn't matter what the base is.
Just greater than 0.
It has to be greater than 0, yes. And obviously that would apply to ln, which is base b. Sure. Yeah, I can, and I want it to be silly, and since today is cloudy and overcast, could this? While you guys are writing, I can be coloring. Just for fun. We don't like our clouds gray. We don't, but today it's gray outside, so I'm just being obnoxious. At least there aren't any lightning bolts coming out of them, right? Not yet, anyway. All right, so let's do some domain examples. Find the domain of the following. Let's say I have, make this A, y equals ln of x minus 3. So what's the deal here? Yes.
What was the number 4?
What was number 4? I'm so happy that you're writing this down. Should I say your name live on tape? I won't.
Please go ahead.
Thank you. All right. So what's the deal here? What's the cloud in simplistic? It's just x minus 3, right? Ln of the cloud, right? So that x minus 3 has to be greater than 0. So can we do a sign chart here? That is what makes it 0. 3. And it has to be an open dot, right? And it's got a positive slope. So here's got a positive slope. And this is negative, and this is positive here. I can only take the log of what kind of numbers? Positive. So the domain is from here to here, so it's okay, B. Y equals natural log of x squared plus 1. What are we going to say? I know, but we're going to do that. X squared plus 1 has to be greater than 0. Does this have any 0? No. So what kind of parabola is it?
A floater.
A floater. It is, absolutely. It's a floater, so where does it live? Above or below? Above. And so my sign chart is all positive, right? So the domain is all real numbers. Tricky, Mrs. Muller. We aren't on a freak out. All right, C. Let's try this one. Okay, so now what are we doing here? Absolute value of x has to be greater than 0. So I'm going to do a sign chart. Where is that 0?
0.
At 0. So I can have that open dot here. And if I were to superimpose that graph, what's it look like? And if I get a sign chart, we get positive, and this is obviously 0 here, and then negative, or positive, sorry. So what is the domain? Right, so negative infinity to 0, union 0 to infinity. Another tricky. Are you looking at other numbers? I prefer your implementation, but yes, I would judge it in the desperation of the last minute. I do. What about this one? Y equals natural log of x squared minus 5x minus 4. What are we going to say? X squared minus 5x minus 4. You see how we've seen inequalities. It's called circular understanding. Can you see if we can remember how to do this? You want to get here? -4? Oh, this must be a plus. So sorry.
Now I can factor to minus 1, minus 1.
Yeah, that's what I meant. I'm sorry. So I'm gonna do the sign chart. What are my zeros? 1 and 4, yes, and there's 0 here and here. And this opens upward. And so my signs are plus, 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 minus, plus, plus, plus. And I can only take the log of positive numbers. So remember that these are open in Logville. Okay, so the domain here is negative infinity to 1 in union with 4 to infinity. 4 to infinity, good. This is going to help you with the problem of the week. Doesn't matter what base it is, I'm going to use element of. What's the cloud?
X, 4 minus X over -1.
X, I'm sorry, let's try again. 4 minus
X
4 minus X over X plus 1 has to be
greater than 0.
greater than 0.
X.
So -1 is makes it open dot, right? That's the, remember this?
Yeah.
Oh, I see what you're doing.
Yeah. Okay, and let's superimpose, so what's the graph at the bottom anyway? The line with a, well, positive slope on top, down the bottom, right? All right, what's the 0 on top? 4. And that's a solid dot, right? And then if I were to graph it, it would be with a negative slope. And now let's do our sign chart. Because it's 0. It's a 0 of the function. I'm only using the sign chart to tell me when it's positive. Greater than 0, okay? All right, so this is going to be what kind of number here? Negative, good. I want to use a different color here. Negative, positive, and negative. So the domain, -1, 2, 4, they're both non-inclusive, right? You can't be 0. Okay.
So that's just like.
This is the sign chart for just this side. Do you know what I'm saying? All right. What do you think? You can do those now, right? So let's graph some. Because usually that gives people heartburn. I don't know why, but f of x equals log base 3 of x. First thing I do is find the domain. Well, what's the domain here? X has to be what? 0 to infinity. So I know what side does it live on? The right side. Where's the asymptote going to be? At x equals 0. Now, here's where I graph 1, 0, and base 1. 1, 0, and base. Did you graph that way, Mr. Johnson?
Yes.
So what's 1, 0?
1,
Right here. And then base is 3. So 1, 2, 3, 1. X equals log base 3 of x plus 3. Where am I taking? First thing I find is the domain. What's the domain going to be? Can we do that in our head? I know you can do it in your head. What makes it 0? -3. So x plus 3 has to be greater than 0. So it's going to be from -3 to infinity. Where is the asymptote going to be? And then it's gonna be 1 in front, and then what's the base? 3 in front and up 1. So 1, 2, 3, up 1. There we go. So I use my asymptote as my reference. What's my reference? It's going to be 1 in front and then 1, 2, 3, up 1. Okay? Moving along, let's do another one. I'll make this base 3 still again. Okay.
How do you choose the place?
I always know that a log graph is going to be 1 in front of the asymptote, and then base 1 and up, base and 1 up from its asymptote. You know how this is 1, 0, base 1? All I'm doing is 1, 0, and base 1 in front of my asymptote. That's how I do log graphs. All right? We're not going to let this creep us out. What's the domain here? It's I know that we're going to have 2 minus x has to be greater than 0, right? What makes it 0? 2 with a solid dot, and then what happens? What kind of slope? Negative. So my sign chart is this. So what is the domain here? Negative infinity to 2, open. Where's the asymptote? At 2. Now, it lives on this side, doesn't it? Is it upside down? No. So I'm going to be 1 in front of the, or back of the asymptote, and then what's my base? 3. So 1, 2, 3, up 1. Okay? If this was negative, it would be upside down. The domain tells me which side of the asymptote I live on. I really like that. Because then it takes the stress out, doesn't it? Perhaps? I don't know. All right, move right along. Let's evaluate some. Let's say I have log base 8 of 64. Now remember, a log is an exponent. So what am I looking for? An exponent. What exponent do I put on 8 to get 64? This is 2. Log base 2 of 8. What exponent do I put on 2 to get 8? 3. Log base 9 of 3. Ooh. What exponent do I put on 9 to get 3? Good. Log base 3 of 1. What exponent do I put on 3 to get 1? 0. You see what I'm doing? This is the exponent you're putting on the base to get 1. Log base 10 of 10. What exponent do I put on 10 to get 10? 1. Log base 27 of 3. 1/3. Then you take the cube root of the base, yes. Tricky one. Log base 27. Oh, no, try again. Log base 9. That's 1 over 27. So if you don't know what it is, you should put an x here and solve. What are we going to do? This would be 9 to the x equals 1 over 27. Got to get the same base. So this is 3 to the second, or 3 to the 2x equals 3 to the minus 3. So 2x equals negative 3, x equals negative 3/2. So even I can't do some of these in my head. Okay? Just so you know. All right? Change the base formula. Do you remember that one?
Oh, yeah.
Oh, but I have an easy way to remember it. I hope. Why do we use this? We use this because you don't have log base 3 on your calculator. Well, you do, but it's hard to find. Okay, so log base 3 of x. Let's say I want to change it to the natural log. The base goes in the basement of your fraction. What's the base? 3. So this is ln of 3, and then the argument goes in the attic. Got it? The argument goes in the attic, the base in the basement. Let's say I wanted to change log base 3 of x to log base 5. What goes to the basement? So log base 5 of 3, and the argument goes in the attic. It's stupid, it's silly, but it helps me. I never forget it. Okay, so let's do the generic. It would be log base b of a is equal to ln of a over ln of b. Okay? I just did it random. Okay, so let's do some estimating. I got 2 minutes. Log base 7 of 50. What could that be approximately? Is it going to be bigger than 2 or? So it's about 2 though, right? Why? Because 7 squared is 49. All right, what about this one? Log base 3 of 10. That's too easy. It's going to be the same, right? Log base 8 of 100. Okay, so 8 squared is what? 8 cubed is huge. So this is going to be 2 point something. Do you think it's going to be closer to 3 or is it going to be closer to 2? So maybe 2.2?
Yeah.
Somebody, did you do it on the calculator?
No.
97.
Hmm?
97.
There's no way.
18, 2.2.
Oh, okay. I thought you were telling me it had to equal 97.
No.
Okay, I feel better. So she's saying that h to the 2.2 is approximately what?
97.01.
97.01. That's pretty close.
And 2.1 and 2.3 are way off.
So 2.2.
2.215.
Good morning. Please stand for the morning prayer and pledge of allegiance. If you're in the hallways, please stop. Today's prayer is for all our families. In the name of the Father, the Son,